Hi there, Alex from Oricon Asset Management team, and
I'm Jerome, also from Oricon Asset Management.
we'll be briefly talking about the paper we are presenting at the AMPEAK with the objective of finding lowest replacement cost of an asset using some modeling simulation techniques. We just sharing here the screen of a paper with some mathematical formula that we are going to be covering shortly. So a number of equations here for calculating equivalent annual cost, the pseudocode of how we do it, and we'll be talking about shortly on the Python and Excel interfaces themselves.
Okay. Let's just jump over to the Excel model.
So the Excel model, in brief, we've got a set of inputs as defined by the paper. We've got weighable probabilities of failure and asset age when it starts the simulation. Once you fail or replace the first asset installed, you may use different weighable probability distributions. We've got cost of failure for the business. So if there is a particular event failure, let's call it 1,000. If I have to replace the asset, it's a fraction of that. So in that particular case, we put a ratio of 1 to 10 here, 1,000 to 10,000. On the set here that is being shown, we are replacing, suppose the asset at a frequency of 50 years. We say we look for a project length of 150 years and a discount rate of a 5%. With this set of inputs, we do generate a number of weighable distributions to simulate what the life of the asset would have been. If this asset life is less than what we are saying being the replacement frequency of 50, we call, well, it failed. So this is being flagged as reds. If it didn't fail and you replace at the scheduled frequency, it becomes a yellow. We can see for a period of 150 years, we've got an event at year 7, another at year 57, 107, then 144. Failure events obviously are the $10,000 ones, replacements at 1,000. We discount these cash flows at the 5% rate we have set, and we got a number of cash flows. As you can see, longer in the future, the cash flows becomes potentially quite negligible. We sum these present values, and we can start talking about the outputs now. We've got 4 events for a period of 150 years. The sum of cost is 7,000 odd, and we've got the last asset replaced at year 144. When we divide the sum of present value costs, the NPV, by the annuity, being 20, we land into a value here, right? So that's our EAC. We run a number of these scenarios, and then we assemble a type of an outcome. So that would look like something like the curve being shown here. It follows the intuition. If we replace too frequently and we don't take much of the life of the asset, becomes expensive. That is like replacement intervals to the left. Replace it rather frequently. Conversely, if you don't replace enough, you might suffer with consequence of failures. Similarly, gets expensive, which means there's a point here that's optimal. And this becomes a convex optimization problem that has a minima. As we can see here, someone might argue, well, the optimal interval has been found as 8 years. Isn't 6 or 7? Yeah, something possibly to that vicinity. It depends on the number of trials and how fast the problem converge. Though on chart might not be that clear numerically. If you run this scenario a number of times, it tends to settle at the year 8. So,
Yeah, so here, so the Excel code did a single one of those iterations, but to do all of those iterations, and here we're do tens of thousands of iterations, the Python code is really a much better place of doing it. And here, this is a Python implementation of the algorithm where we have implemented all of the math equations are implemented here. It gives you the ability to just configure a scenario, you pass it along, and it gives you the outputs. So here, this is where you would define your own assets and see what would happen over its lifetime. Well, thank you very much for listening to us today. We looking forward to seeing you at AMPEAK.
Thank you.